All right, this week we're going to be talking about the signal detection theory, and that's looking at a person's response bias and when they decide whether a signal is there or isn't there. So, talking about the signal detection theory, we're separating sensitivity from response bias. What criteria is the person using to respond? Are they using a strict criteria where they're waiting until they're absolutely sure that they hear that response? Or are they using a more lax criteria where they respond even when there's nothing there, they're just guessing? So we have several outcomes. We have a hit, which means that the signal was present and the person says the signal was present, and that's our sensitivity. We have a correct rejection, which is where the signal was absent and the person says it was absent, so that's specificity. Then we have a miss, where the signal is present and the person says it was absent. We present something and the person doesn't respond. Or a false alarm, where the signal is absent and the person says it was present. That's a false positive, meaning that we didn't present anything, but they raised their hand or indicated that they heard something. We can look at this a different way. If we start in that 11 o'clock position and move clockwise, we have a hit, meaning that the signal was present and it was detected. Or we have a miss, moving clockwise, meaning that the signal was present but it wasn't detected. And then at about 3 o'clock, we have a correct rejection, which is where the signal was not present and the signal was not detected. And then moving over to the lower left quadrant, we have the false positive, meaning that the signal was not present, but they said it was there or they detected something. We have some assumptions with the signal detection theory. There's always some degree of noise present. There's environmental noise, a truck driving by, an airplane flying overhead. There's instrumentational noise. Maybe there's a little bit of line noise or a little bit of a hum. There's physiological noise, heartbeat, breathing. There's muscular movement, so when they move around, that can play a factor. So the noise is going to be a part of this task. It's inherently there. The stimulation of the auditory system varies continuously, and noise is random. So all of these factors come about, and all stimulation then is going to occur along a single continuum. Is the stimulation of the auditory system due to the noise alone? Or is it stimulus plus noise? So they're just sitting there and there's noise present, so that's the noise alone. But then we also have the noise present because it's always there, plus the signal that will be there as well. So here's something that I pulled from the Journal of Neurophysiology, and the article is referenced there at the bottom. And we have our little continuum again in a graph, which is, or a table, which is nice to see. So in the first row, we have the signal absent, and then we have the answer that the signal was absent, so that's a correct rejection. Or we have an answer that the signal was present, and that's a false alarm. And then our second row, we have the signal present, and again, we have the answer that the signal was absent, so that's a miss. And then we have the answer that the signal was present, and that's a hit. So we can also graph these, which makes it easier to see. We have the stimulus intensity along the x-axis and the probability of response along the y-axis. And we have the noise distribution here. And then we have the signal distribution here. And there's going to be some overlap there. And you can see that here. And then we have our response criterion, which can move along that x-axis depending upon whether we have a lax response criterion or a strong response criterion. So looking at the noise versus signal and noise decision, it's represented along the x-axis showing the magnitude of sensory activation or energy. And the N is the probability, or the noise is the probability of occurrence of noise alone. And then the signal to noise is the probability of the occurrence of the noise plus the signal, like we talked about before. And there's always more energy in the signal to noise than the noise alone, because obviously the noise is always there, and then you're adding that signal, so of course there's going to be more energy there because you have that added signal energy. And then we have a separation between the noise and the signal to noise, and that's the measure of the unbiased sensitivity. So as we look at the observers, we have an ideal observer where the criterion matches, the criterion minimizes the misses and false alarms. So minimizes when they have a signal present and they say there's nothing there, or when there's no signal present and they say there's something there. But the real observer is affected by his knowledge of the task. So will he adopt a strict or lax criterion based upon the instructions? And the instructions are very important. I'm sure you've heard in clinic when you're asking a person to respond. Some people will not respond unless they're absolutely sure. And so then they will report fewer signals because they're using such a strict criteria to respond. In this graph, you can see the noise distribution on the left and the signal plus noise distribution on the right, and we have our criterion response. So you can see there are the hits, and then there are the misses. And then we also have false alarms in the bottom and correct rejections as well as part of the noise distribution. So at the top, we're looking at the signal and noise distribution, and at the bottom, we're looking at the noise distribution where there is no signal. So you can see as you move that criterion response along that x-axis, you can increase the misses and decrease the hits, and you can also increase the correct rejections and decrease the false alarms by moving to the right. So we can look at D prime, and D prime is going to be the separation between the noise and the signal to noise curves. And D prime equals the means of the signal and noise signal to noise distributions divided by their standard deviation. The greater separation, the larger the D prime value. And it's assumed that the noise and signal to noise distributions are normally distributed with equal variances. And then your criterion is the vertical line drawn along the distributions. So if the energy is greater, then the criterion response is going to be a yes. And if the energy is smaller, then the criterion response is going to be a no. So here you have the noise distribution and the signal to noise distribution, and you can see D prime or sensitivity there. And it measures the ability to discriminate a stimulus from a noise, and it's represented as the distance between the means of the signal and the noise distributions like we talked about. And then we have the response bias, which indicates the amount of evidence needed to accumulate and make a response in yes-no responses. We can look at this in terms of ROC curve, which is a receiver operator characteristic, and we plot the distribution of hits versus false alarms for each criterion point. And it illustrates the effects of sensitivity and response criterion, like we just talked about. And sensitivity is going to be the distance of the receiver operator characteristic from the diagonal, and the response criterion is the particular point on the ROC curve. And I'm going to show that to you because it's easier to see in a visual. And this is pulled from a study that was looking at eyewitness identification. So we have, we're looking at memory strength, but we could use this to look at responses to a tone just as easily. In the graph on the right, you can see the false ID rate along the x-axis and the correct ID rate along the y-axis. And that's how you plot your ROC curve. So correct responses versus false alarms. And so that's plotted there. And on A, you can see a liberal response, meaning that their response criterion is moved a little bit to the left of our graph, and it's plotted there. And then B is neutral, so they're kind of in between. They're not liberal and they're not conservative. And that's plotted on our ROC there. And then we have a conservative where our response criterion is moved more to the right on our graph, and you can see in the ROC it plotted here. So we can have a strict criterion, meaning that the subject has a great ideal of confidence in the decision before willing to say yes. And we can have a lax criterion, where the subject does not require as much confidence before a yes response. And then the confidence ratings enable the examiner to obtain several points simultaneously. So you can ask the subject to rate their confidence in each response to help you plot this. So we have several scenarios. We have no false alarms, where the noise and the signal-to-noise graphs do not overlap at the criterion, and the D prime is said to be 3 or 4. And the hits equal the false alarms means that the signal is not detectable and they're guessing. So if you have the same number of hits as you do false alarms, they're just guessing. And if the false alarms are greater than the hits, then you need to re-instruct them definitely.